Alright, welcome to your advanced algebra notes from spring break. I'm currently in Arizona and my kids are currently sleeping, which is why I'm talking quietly and probably sound a little bit creepy. Anyway, you all know me. Oops, let me put it on pen there. I am Tim, or Mr. Stapert, or T-Stape, or whatever it is that you normally call me. We are starting Chapter 9 today, and Chapter 9 is all about exponential growth, which happens to be something we've already encountered. You remember that wonderful, all-important, life-changing formula? And I actually don't say that terribly sarcastically, it's actually true. That formula about the amount that you would have if you started with a principal and you allowed it to grow at a certain rate for a certain amount of time. That formula, the interest formula, where we had a rate and a time, where time was kind of our independent variable, the more we left it alone, the bigger the amount that we actually had. So we could figure out, if we had, say, $1,000, and, oops, I totally did that backwards. If we wanted to figure out how much we would have, and we started with $1,000, the principal amount there, and say we were to earn the stock market average of 10%, 0.10, and we were to leave it alone for 5 years, how much would we actually have? You could plug that into your calculator, and you would see that after 5 years you'd have $1,610.51. Yay. That's actually a really good interest rate too, 10%. And so if you were to this summer, make $1,000 and put it away somewhere and leave it alone, and you average 10%, which is again far better than you can do by putting it in the bank or anywhere like that. If you invested in the stock market and you earned the stock market average, now there's a big if in there, your $1,000 could turn into $1,610, which actually doesn't seem like maybe a huge growth to you. You'd leave it alone for all those years during college and you'd make $600 off of it. Not the world's most exciting thing necessarily. But that's just it. Exponential growth, if we have an equation that is defined, equation f defined by the equation f of x, a times b to the x power, where x is our independent variable, that is an exponential function. The thing is here is that I like to call it like a mathematical explosion, but so a function that has that variable, like our time t that's in the exponent there, it is an exponential equation, and really it grows really fast. And now my previous example there probably didn't look like it grew that fast, so I thought it'd be fun and hopefully somewhat powerful. I know you've seen these examples before a little bit, but I thought it'd be fun to graph it and just see what that looks like. And wouldn't you know, oh, look at that, there's a graph down here. Somebody thought ahead and put together a graph here. So t, your time in years, and your amount. So t is like our x, it's our independent variable, and the amount that we have in our account. So again, I'll just write that equation over here again. Amount equals the principal, and we're starting with 1,000. So that was our principal amount. Ooh, principal or principal? Principal. That was our principal amount, and we are earning it 1 plus. We're going to just say we're going to average 10% per year. Again, stock market doesn't normally actually return 10% a year. Some years it's a lot higher, some years it's a lot lower, but it averages about 10% a year. and we're going to leave it alone for t, the amount of time, which again is kind of like our x variable. It's our independent variable. So how much money would we have after a period of time? And you'll see why it's called exponential growth and why I said it grows really fast. It's kind of an explosion. It takes some time, and initially it's kind of boring. So you saw the first one there. After well, I could start at time 0 here, I suppose, and I'd say I have $1,000, so that's like that point, like right there. After 5 years, it's only grown a tiny bit, and that's like maybe that point right there. After 10 years, it's grown a little bit more. We're up to 2,500, 2,593. After 15 years, it's grown up to $4,177. So we're getting closer to 5,000, although so far it's not terribly exciting, that graph. It's growing, well, pretty slowly. After 20 years, we finally break that 5,000 barrier. We're up to 6,700. That'd be right about there. I'll skip ahead a few so we don't have to do every single one here. But after 30 years, now we're starting to see something exciting. We're up to $17,449. Starting to grow a little bit there. Although still, I mean, this was $1,000 you put in when you were, 15 years old, and now you're 45, and it's grown to 17,000. It's a decent chunk of money, but it's maybe not, it's a car. It's not anything that exciting. After 40 years, though, now it's growing a little bit more because we're gaining that interest on interest. This is why it's exponential growth. And we're actually up to $45,259. So just above 45,000. And now you're starting to see the pattern, I think. Because after 50 years, I'm going to have trouble following this one. After 50 years, we've actually grown to, so this is, you did it when you're 15, this is when you hit 65. That $1,000 has turned into $117,390, which is actually off my graph here. So, I'm going to have to keep scrolling, if I can. I think there was somebody who was nice enough to put marks all the way up to $120,000. So somewhere around there. I hope I got the right line there. I think I'm off by one. Let's erase it and redraw it. There we go. So you can see graphically why we call it kind of an explosion. If I were to draw the connecting points here, oops, there we go. Oh, I kind of missed my point a little bit, but you get the idea. It's going to go up and up and up and up and up and up, and it starts to grow incredibly rapidly. And just for fun, there we go. Now I connected. Not the greatest drawing I've ever done, but just for fun, I thought I would calculate what would happen if I left it for 60 years. So 60 years until I was 75 years old. That original $1,000 would turn into $304,481. That's a house. Your summer vacation money this summer just turned into a house. Now there's some other realities like inflation that'll eat at that a little bit. And there's the reality that it won't actually grow nice and smooth like that. It'll probably grow more like this. If you look at the stock market, it probably looks a little more like, big jumps like that, up and down, up and down. I know that was not pretty, but you get the idea. But exponential growth has some really important ramifications for your life. If you understand that chart and that exponential growth eventually grows really, really fast, it can have profound impacts on your life. It actually, incidentally, is a big problem with trying to solve some problems on a computer. If you're trying to, the classic problem is the traveling salesperson problem, trying to calculate the fastest path between points, and I won't get into the details, but if you get more than a few number of points that you want to visit, it's an exponential problem, and it becomes impossible for a computer to solve. But anyway, let's look at the problem that you've got in your notes here, because this is another area where you often see exponential growth. It has to do with biology. So the population N of a certain strain of bacteria grows according to the equation N equals 200 times 2 to the 1.4 times T power. And so because T is the independent variable, and that is in the exponent, we have an exponential equation, and we're using T. As you can see here, T is the time in hours. So how many bacteria were there at the beginning of the experiment? Well, at the beginning of the experiment, the time was 0, so let's zoom in so I can draw this a little bit better. Our formula, if you remember, is N equals 200 times 2, so it's doubling every 1.4 to the T. So after 1 hour, less than an hour, it'll more than double. But our T at this point we said was 0, so 1.4 times 0, we end up with 200. We just plugged in that 0 for T, in case you're having trouble following along here. So 200 times 2, 1.4 times 0 is 0. 2 to the 0 power is 1. So 200. So how many bacteria were present at the beginning of the experiment? 200. Now the next question is, after how many hours will the number of bacteria double? So how long will it take before the bacteria in here double? And so what we're looking for is, when will this equal, when will it, we started with 200, when will we have 400? Well, it's going to equal 200 times 2 to the 1.4 T. So we got to figure out when at what number of hours there, at what number for T there, will this equation be true. So how do we solve for that? There's a couple different ways to do it, but I think the way that I would think about this one is that, look, I need this whole number here to equal 2, right? Because 200 times 2. So that would mean that this up here needs to, this 1.4T actually needs to equal 1. So does 1.4T needs to actually equal 1. Because when 1.4T equals 1, this whole thing would be 2, and this equation, it holds true. And if I think of it that way, it actually becomes really simple for me to solve it quickly. So I can divide both sides by 1.4. And so I get T equals 1 divided by, oops, let me punch this in my calculator right here, 1 divided by 1.4, or 0.71, we'll just 714. So how much time would it take in hours? A little less than, I guess it's a little less than 45 minutes there. So T would equal that. Estimate the number of bacteria after 10 hours. Well, we've got the formula for that, so we can do that. What would the number of bacteria be? 200 we started with, times 2 to the 1.4, and now we're doing T as 10. So I could think of that 200 times 2 to the 14th power. 200 times, I'm just punching this in my calculator, 2 to the 14th power. There would be roughly 3,276,800 bacteria after just 10 hours. We started with 200, and after 10 hours we're already up to 3 million. That's that mathematical explosion there. And then lastly, estimate the number of bacteria 2 hours before the experiment began. That's kind of a fun one. So we want the number 200 times 1.4. Now our t this time is 2 hours before the experiment began. Can I do that? Sure. Why not do it as -2? So what I get there is 200 times 2 to the 1.4 times -2 is -2.8. And if I punch that into my calculator here, 2 to the -0.8, we would see that there was 2 hours before the experiment began, we had 28, it's 28.7, so I'll round it up to 29. Only 29 bacteria before the experiment began. So actually, if you think about it, from 2 hours before the experiment began to 10 hours after it began, we went from 29 to 3,276,800. That's a lot. That's exponential growth. So anyway, I hope you enjoyed that video. Your homework, as you can see at the bottom of the page there, is worksheet 9.1. Enjoy.